everybody. We're pleased to have you here for the second of three webinars in analyzing and accessing 2020 census and the 2016-2020 ACS data using R. This is a webinar series for teachers and researchers, and we're very pleased to have with us Dr. Kyle Walker, who is the unabashed expert on all of these matters. He is the author of the book Analyzing U.S. Census Data, Methods, Maps, and Models in R. We'll have a lot of that information for you. As I said, this is one of three webinars that we're doing in this series. The first one was last week, where we looked at just generally analyzing 2020 census data with R. Today is going to be making maps with the 2020 census in R. And next week, for those of you who want to also attend, we're going to unveil, probably for the first time in the country, how to analyze the 2016 to 2020 5-year ACS, American Community Survey data in R. Those data will have just been released a few days earlier, so this will be a chance for you to really get going on that. But today, the mapping webinar is one of great interest to a lot of people. And Kyle has a lot of experience doing this. I just want to mention that these webinars are organized by the Social Science Data Analysis Network, SSDAN, at the University of Michigan in our Population Studies Center. We've been around for quite a while, since really the mid-1990s, and our idea is to make demographic data accessible to the general public. And in various different undergraduate and graduate courses, we do webinars, we do summer workshops, we have a lot of things on our website, ssdan.net, that tells you a lot about our project, which is supported by NICHD. So, we're very pleased that you're all here today. We're very, very pleased to have Kyle with us for the second one of these three webinars. And I'm going to pass the baton over to John DeWitt, who is going to say a few introductory remarks before we bring Kyle on.
Sure, thank you, Bill. So as Bill mentioned, this is the second of three webinars we'll be hosting this month with Kyle. Please look out for additional emails next week for the third in the series. As Bill mentioned, the 5-year ACS estimates are just coming out this week. So it is quite timely that we will have Kyle next week able to show how to access those estimates in R. Also want to quickly just give a little bit of an introduction to Dr. Kyle Walker, who is an associate professor of geography at Texas Christian University. He has developed multiple R packages that, as Bill mentioned, really makes him, the go-to expert for all things related to accessing census data and analyzing census data in R. So without much more ado, I will turn things over to the person who you came here to see, Dr. Kyle Walker. Kyle?
Yeah, all right. Well, thanks, Bill and JP, for the introductions. Much appreciated. I'm going to go ahead and share my screen and walk you through how to get started with the materials for today. And we can go ahead and get moving. So share right here. All right. So what we are looking at with respect to kind of getting set up is the general content for today. So today's workshop covers mapping 2020 US Census data in R. And so we're going to do a broad overview over the next 3 hours of everything from basic GIS and geographic data handling to making kind of interesting exploratory maps to really dealing with cartography in more sophisticated ways, all using R and all using sort of automated data pulls from the US Census Bureau. And so a little bit of background information. Appreciate the introduction from Bill and JP. I have been at TCU now for 10 years at teaching and researching in geography. work broadly as a consultant in spatial data science, as well as kind of various sort of computational demography type topics. But really where my passion has been over the last few years has been developing R packages. So I'm kind of mainly focusing on developing the tidycensus and the tigris packages, which you're going to learn both of those today for working with US Census Bureau data. I've created a number of other smaller packages. Mapbox API includes a variety of different functions for working with Mapbox web services in R. And Bill also mentioned my book, which is linked in the slides here. I'll show you how to access the slides directly if you need them. That book is available for free online right now, and it's going through an interesting revision process right now. Basically, the book is content-wise in pretty much its final stages, but I'm going to do a wholesale overview, a wholesale update of the content for the brand new census and ACS data that you're getting an introduction to over the next couple of weeks before it's published this fall. And so this is the second of 3 workshops in the SSDN workshop series. Last week, we covered an introduction to 2020 US Census data. And all of that content, if you did miss it last week, is fully available to you. And I want to show you how to get it and to use it in just a moment. Right now, we're covering mapping 2020 US Census data. And then next week should be really interesting because we're going to do a first look at the just released, as of yesterday, 2016 to 2020 American Community Survey estimates. Typically, these are released in December. It was delayed to March due to the COVID-19 pandemic. And so we're all really excited to have some new data to work with. So today's general agenda is divided up into 3 sections. And so basically what we'll be doing is we'll be going section by section, take a short break at the end of each section where I'll give you some exercises that you can work on. And then we'll come back typically at the start of each hour and reconvene. So the first hour is all about census geographic data. Before we can make maps, we need data. And what is geographic data? And what is census geographic data in general terms? We're going to be going over that. You're going to be learning some basic GIS or geographic information systems terminology to really get you up and running. Hour 2 is all about then making maps. You're going to be introduced to the TMAP or thematic mapping, ARM package for GIS style cartography. So we're going to go through a variety of different options for making maps of 2020 US Census data. And then finally in hour 3, we're going to cover some more advanced topics. So ideally, kind of we're getting comfortable, we're starting to get introduced to the tools in R for map making. Now let's really start to think about leveling up and consider more advanced topics such as interactive maps and advanced geometry handling, which I'll explain in greater detail when we get there. So first and foremost, to get started, there are a couple of different ways that you can follow along live today. So if you'd prefer to just watch and then try it out later, you can. If you'd like to follow along live, that's very much encouraged. And there are a couple of different ways that you can accomplish this. So the different ways in which you can follow along are found on the GitHub page, which JP provided the link to. It should have been sent out to all participants as well. If you need it, what you can do is go to github.com and search for my profile, Walker KE, and you're going to look for this repository, UMich Workshop 2022, or you can Google that and it should come up. And so what we're looking at here is all of the information you need to get started, both for new users and more experienced users. In fact, what I'm going to do right now is I'm going to pop that link directly into the chat for all participants. And so that link is in the chat. You can go directly to this site. And so on this site, there are a couple different things that you can do. You can access today's slides. Today's slides are hosted on my website. You can access them there, and you can indeed even copy paste code over to R if you want to. If you're an experienced R user who already has R and RStudio installed, what you can do is two things. One, if you're familiar with Git, you can clone this repository to your computer. That will pull down onto your computer all of the code that you need to run today's workshop. If you are less familiar with Git, but you are familiar with R in RStudio, you'll click in this mapping census data folder, and you'll find this file code.r. This includes all of the code that you need to run today's examples. If you are new to R or less experienced with R and don't have it installed on your computer, I have set up for you an RStudio Cloud environment where it's pre-built, all the packages are installed, and it's pretty much ready to go. And so what you can do with RStudio Cloud is click this link. I'm going to open it here in a new tab, and it'll take you to the login page. If you don't have an account, you can sign up for an account. It's free. You can even authenticate with an existing Google account. I'm going to click login with Google. I'm going to choose one of my Google accounts. And what that will do is take a few moments to build the project environment. This is an environment that I have pre-prepared for you that you can basically just go in and get right up and running with the examples for today. So this will take just a moment to build. And once it's built, you'll notice here, there's a kind of a bunch of stuff that's coming through. I'm going to clean this all up a little bit. So if you find this little broom icon right here that says clear console, I'm going to click there. And this little broom icon that says clear objects from the workspace, I'm going to click there and click yes. So now I have a blank environment in RStudio Cloud. And so what I'm going to be doing here is a little bit of organization. First and foremost, you'll notice that it says temporary copy. This means that your information is not going to be saved. I'm going to choose save a permanent copy, which will copy this over into my personal workspace in RStudio Cloud so that it'll be saved for me to use at a later date. I'm now going to move a couple of things around. You see this little window pane icon? I like to have my R console on the right-hand side, so I'm going to click there and choose console on right. I now have 4 panes within RStudio that I can work with. I have a script editor. I have a console where I can type interactive R commands. I have an environment pane, which I'll populate a little bit later, and then I have a files browser. In my files browser, I'm going to want to click mapping census data, and I can open the file code.r. And that's going to open what's called an R script that gives you all of the code that's necessary to run the examples for today. Lines with number signs in front of them are commented out, which means that you can run that code if you want to, but it's set to bypass it. It's not firmly necessary for today. And in some cases, I'll show you at times when we will uncomment some of these lines. So this is what you need to get started. If you're familiar with R Markdown, which is sort of a notebook style format for working with R code, you can actually run the code straight off of the slide deck that I created if you're a little bit more comfortable. But we're going to work here off this code.r. You can do a variety of different customizations to RStudio as well by clicking Tools, Global Options. If you want to change the appearance, maybe a dark theme is your preference, you can choose a different editor theme, and you can also choose a different editor font. I'm going to keep the defaults for today. So with that in mind, I'm going to go ahead and jump back to the slides, and we're going to go ahead and get started. So in part 1, as mentioned before, we're covering census geographic data and GIS in R. And I want to give a little bit of a brief overview of what census geographic data is like. So we covered this last week for those of you who were able to attend. If you didn't attend, what we're going to be talking about today are ways that the US Census Bureau aggregates data. So typically when we acquire data from the Census Bureau, we get data that are tabulated at a variety of different census geographies. And so those geographies ultimately kind of allow us to focus on specific locations when we're analyzing data, and also look at demographic patterns at a variety of different spatial scales. And so this diagram is a graphical representation of the census hierarchy of geographic areas, and broadly covers a number of geographic areas at which the Census Bureau aggregates data. The core census hierarchy is this central axis of the diagram, in which we start at census blocks, which is the smallest geography at which census data are available. And then each child unit in this core census hierarchy in the central axis nests or fully composes a single parent unit in the next level of the hierarchy. So census blocks are the smallest geography at which census data are available. They're roughly analogous in many cases to city blocks. Block groups are then geographies that tend to have maybe 800 to 2,000 or so people in them, and they're fully composed of blocks. Census tracts are then the next level up that average out at about 4,000 people per tract, and they are fully comprised of block groups. Census tracts then nest within counties, which then nest within states, and so on and so forth. And there are a lot of other geographies at which the Census Bureau tabulates data. So if you attended last week, you learned about how to acquire data for these different geographies, but the geographies themselves need to be defined. They need to have actual boundaries that are maintained by the Census Bureau. And those are found in the Census Bureau's Tiger Line database. So Tiger is an acronym that stands for Topologically Integrated Geographic Encoding and Referencing, but Tiger is a much nicer way of putting it. And so the Tiger Line database is maintained by the Census Bureau as its sort of master repository of shapes at which all of the census data are tabulated. And the Census Bureau also makes available to us, the public, for free, Tiger Line shape files, which are a common geographic information systems data format that can be used in a variety of different software applications like R. Typically, what GIS or geographic information systems analysts will do when working with these Tiger Line shapefiles is they will go to the census website and either use a link or a drop-down menu to identify locations that they need, download that information. Here we're seeing counties in Colorado, and unzip a zipped shapefile, and then load that shapefile into a desktop geographic information systems, platform of your choosing. And so basically what you would typically do in this particular context is you could browse around your data in a desktop GIS. And here we have, Summit County, Colorado highlighted. What we're focusing on today is a package that I've written called Tigris that functionally takes this entire process and makes it seamless in R. So instead of having to go in and do the data identification and the downloading and then the unzipping and then loading that into your GIS, Tigris takes care of all that for you in R. And so I'm going to show you briefly kind of how to get up and running with Tigris. I see one comment in the chat that it would be helpful to revisit how to get up and running. So there's two pieces here. We're not going to cover installing R, installing RStudio. If you're using your own version of R or RStudio or your own computer, it's we don't have time to go through all of that. What I would recommend for users who are brand new to R, just to retrace the steps a little bit, what you're going to want to do is find the link in the chat that takes you to the basically web page for this workshop on github.com, UMich Workshop 2022. You're going to want to scroll down and find this link that says RStudio.cloud. What that's going to do when you click that link is take you to the rstudio.cloud website. What you'll do if you don't have an account is you're going to sign up for an account, and you can sign up for that account with an existing Gmail account if you have it, or you can just put in your name and then a username and password. It's pretty quick to set up. Once you have that set up, you're going to be taken over here to our Studio Cloud, and it's going to take a few moments to build your project environment. This is basically, I've already set up R for you. I've set up all the R packages for you. You're just going to wait for that environment to build. And once it's built, you'll see a flag up here that you don't see right now, but you'll see a flag up here that says temporary copy, and then a button that says save a permanent copy. You'll want to click that to save it to your account. And then what I've done since then is basically done a little bit of configuration inside of our studio to get started. I have navigated to this folder, mapping census data, and I've clicked the code.r file, which opens up that's the code for this workshop in the RStudio script editor. One other modification I did to the default is I clicked this little window button for workspace panes, and I chose console on right because it defaults to console on left. I like it better on the right, so I'm going to move it over there. And then the last thing that I did was I clicked this little broom icon to clear my console, because by default there was a lot of other stuff coming through that could be a little confusing to new users. That just cleans it up, and ideally we start with this blank clean workspace. And that allows us to get started. So what we have here, going back to the slides, is very basic usage of Tigris. So what we'll do is we will go back to the script here, and we're going to load in the Tigris package with library Tigris. To run code in RStudio, you can do one of two things. You're going to highlight the code in your script editor, and you're going to either click the run button or use, if you prefer a keyboard shortcut, Control-Enter to send that command to your R console. So I'm going to go ahead and click run, and that will load in the Tigris package to my R environment, giving me access to all of its functions. You get a note that says to enable caching of data, set options tigris_use_cache equals true. We're going to cover that in just a moment. To run Tigris, all you need to do is use a function that corresponds to a particular census geography. And by calling that function, what Tigris will do is communicate with the Census Bureau website and pull in the appropriate spatial data set for a given custom geography. So here I'm saying, give me all the shapes for the state of Texas for counties, and assign to it using R's assignment operator, which is this arrow sign, which is basically greater than and then dash. Assign it to an object named TX counties. So let's go ahead and run that through and see what we get. It downloads near instantaneously. And so when we're looking at our data, we can do a couple things. We can inspect our data, and it will print out really what the internals of the data look like. So I'll talk more about spatial data models in R in just a little bit. In the meantime, what I'm going to cover very briefly is the general structure of the object. What we have here is something called a data frame, which is kind of a rectangular data structure for representing information in R. I'm going to type that in and print that out. So all of these columns that you see are going to be attributes of your data. And this is just the default information that comes in from the US Census Bureau data. We have a bunch of different state and county codes. We have the county names. We have latitude and longitudes of the center point of each county. We have land and water area. And then we have this geometry column, which represents the feature geometry of the object, which I'll explain more in just a moment. This is one way of looking at things, but you're probably more interested in actually looking at shapes. And so we can plot that geometry column by using plot Texas counties $ geometry to make a basic plot of the data. And here you go. This is what the counties of Texas look like. And so basically what we're doing here is we're streamlining the process. We are saying, give me counties for Texas, and we can get that information near instantaneously, and then already start to plot the counties in Texas, all 254 of them, and take a look at their characteristics. So a little bit more about the underlying general structure of what you get back. So for those of you coming from a GIS background or who are new to spatial data entirely, the core sort of data object in R is called a data frame. And then you'll occasionally work with package-specific versions of data frames, like the tibble, which is used in the tidyverse suite of tools, or data tables, which is used for the data.table package in ecosystem. But a data frame is basically a rectangular data set comprised of rows and columns. And so typically for a spatial data set, like the one we're working with here, each row is going to represent a single geographic unit, which in this case is a county. And then each column is going to represent attributes or characteristics of those counties, such as its name or its area. And so that's what we refer to with respect to a data frame. In GIS data, if you've worked with geographic data before, you may be familiar with the general model of geographic data, which is comprised of both geographic features and attributes. So we have all of the attribute information, like the name and the area, that you would find in a typical data frame or table of data, but you also have that all-important geometry column. The geometry column, if we go back and take a look at it here in R, you can see numbers. And I can even print out the very first entry here. And you kind of see what's going on here. What it's comprised of is a sequence of coordinate pairs. And so you can think of these as, well, really what they are: longitude and latitude, X and Y coordinates, each of those representing a single point. And this sequence of coordinates for each county, what that does is it functionally works like connect the dots. So in a child's book, and it's sequenced in order. And if you were to connect the dots for all of those different locations, what's going to happen is what's going to happen basically is you're going to get the shape of that particular object. And that is implemented in the SF package, which stands for simple features, which is really the main there are a lot of GIS software packages in R, but SF is really the main one. And SF implements a simple features data model for what we call vector geometries, which I'll cover in greater detail in just a moment. But it really allows for seamless GIS data modeling and representation in R in a really exciting way. It's basically like, take your existing R objects and you can work with them much like you would work with any other general table of data in R, but you have this extra geometry column too that allows you to do GIS work on top of that. And so let's talk a little bit more about that general structure of a simple features object. So if we look at our object here, you'll see where it says simple feature collection with 254 features and 17 fields. So if you're coming from a machine learning background, features are often used to refer to columns in a data set. from a geography background or a GIS background, features are used to refer to spatial units or geographic units. So 254 features in this case means 254 counties. The fields then refer to the columns. So it's basically saying it has 254 rows and 17 columns. The geometry type is something called multi-polygon, and Tigris will typically return objects of type multi-polygon. And I'll talk a little bit more about what that means in just a moment, but polygon and multi-polygon mean enclosed shapes, and that's what counties are. So I'll elaborate on that in just a moment. Dimension XY just means that we are working with kind of horizontal data. We don't have a vertical component to it. There's not a Z coordinate. The bounding box you can think of as drawing a box from the minimum longitude value and the minimum latitude value and the maximum longitude value and the maximum latitude value of the data set. And that will form a rectangle. That is what we call the bounding box of the object. The coordinate reference system, NAD83, that tells you about sort of the underlying way in which the data are referenced to the Earth's surface. This is a more complex topic that we'll touch on briefly toward the end of the workshop. So you see all this stuff, and if you're brand new to geographic data, it can seem a little intimidating at first because there's a lot. In geographic data, there's a lot that we need to do to represent it. It's not just a bunch of numbers. It has to be numbers that are specifically referenced to a model of the Earth's surface such that they can be displayed correctly. Fortunately, the SF package handles a lot of that for us, and we can really focus on the data. So jumping back here, let's talk through some data sets that are available in the Tigris package. There are three general families of data sets that you can get from the Census Bureau. We have legal entities. Those are going to be geographic units that have legal significance in the United States. So it's going to be maybe the boundary of a state or the boundary of a county. Statistical entities then are also bounded units in most cases, but they're units that don't have legal standing in the United States. So they're just used to tabulate Census Bureau data. A good example of that is a census tract or a census block group, which I mentioned earlier. And then we can also get in the Tigerline database geographic features. So these are a variety of geographic data sets that are maintained and provided by the US Census Bureau that are helpful for thematic mapping and in some cases data analysis, but they're not used for demographic tabulation. So you can get roads, you can get water, you can get railroads, and a number of other data sets. And Tigris aims to provide access to all of these data sets. So let's step through some of these examples and talk about different geometry types. So I mentioned before, vector spatial data. Those are going to be spatial data that we consider to be discrete. They exist in one location and they don't exist in another location. So you can think of those as shapes that can be represented as discrete features pretty well. So a county, a census tract, a railroad, those are all geographic features that don't exist everywhere. And so we use the vector data model of points, lines, and polygons for that. Typically, when you're working with census data, you'll be working with polygons, and polygons are bounded shapes. And so in this particular case, I mentioned a census tract, loosely analogous to a neighborhood. We can pull down with the tracts function in Tigris. And we can pull down tracts for a single state at a time if we want to, or we can also grab, say, a county within a state. And so jumping over here, I can run this through and pull down tract data for Travis County, Texas, which is where Austin, Texas is located. And I get all of the census tracts for Travis County. You'll notice here that the message that it tells you is some of the internal translation that's done. So Tigris defaults to the 2020 census shapefiles at this time, though 2021 is available. And you can get files for different years by specifying a different year. It says using FIPS code 48 for state Texas and FIPS code 453 for Travis County, What that means is that the data sets themselves are identified by FIPS code. So if you were to go to the census website and try to download it from their FTP server, you would need to find census tract information for state 48, which is the code for Texas. But I have trouble remembering these codes. I imagine that most people do as well. It's part of the reason why I wrote this package, frankly. And so what Tigris does is it translates state names, state codes, and to state codes internally, and county names to county codes internally. So these are polygons. Polygons are, again, bounded shapes. And you saw the geometry type multi-polygon earlier. A multi-polygon you can think of as an extension of a polygon that allows disjointed shapes to belong to the same feature. So think, for example, of Hawaii. If you have Maui County, Hawaii, and Maui County, Hawaii is comprised of actually 4 islands, not just the island of Maui. But if you're representing a county, you want all of those islands to belong to the same row in your data set, even though they are geographically disjoint. And so that's what a multi-polygon allows for. We can also run through linear features, such as roads for Travis County. And so here I've pulled down all of the roads for Travis County. Typically, roads, rivers, railroads, oftentimes features that you'll use for routing are going to be represented as lines. So as opposed to polygons, which have a perimeter and an area, lines have a length, but they don't have an area. So they're one-dimensional objects. We can also pull in point data. Point data are 0-dimensional features. These are going to be specific locations. There aren't that many point data sets that we get from census. There is the landmarks data set, which has schools and hospitals and stuff like that. It's not a comprehensive point of interest data set, though. It's something that's used by census enumerators to kind of guide their work. So it's a less useful data set, but it's useful in this case to show you kind of a representation of point data. And we'll get into actually mapping point data a little bit later in this workshop. And so we've talked about this already a little bit before, but just to sort of summarize in this section, when you call a tigris function and you're just saying, give me counties for Texas, there's a whole process that happens under the hood. What tigris is doing is it is communicating with the Census Bureau website to get the specific data that you want. It then downloads that data either to your computer, specifically to a temporary directory by default, stores it there, unzips the zipped folder, and then loads your data into R as a simple features object. And so one nice feature in Tigris is options tigris use cache equals true. And what this allows you to do is, instead of downloading data to a temporary folder, it'll download it to a permanent folder on your computer, so that in future sessions, you actually don't have to re-download data. As you've noticed, for the data sets we pulled down, it's pretty quick to download, but for other data sets, like if you need census blocks, those are really big files. And so caching those data sets ends up being really helpful. So let's run through a few different features and options in Tigris to kind of close out this first session of the workshop. By default, the tiger line shapefiles that you're going to pull in with Tigris are the official kind of census tiger boundaries. And so that includes water area 3 miles off the coastline for all of your geographic features. And so occasionally I'll get this question. People say, well, I pulled down counties for the state of Michigan. Why does Michigan look so weird? This doesn't look like Michigan. And that's because the core tiger line shapefiles include this water area. And so we can go over here and try this out. Let's pull down counties for Michigan. And you see this here, especially the Upper Peninsula, it's not really visible because Michigan is almost entirely surrounded by the Great Lakes. And we have significant Great Lakes area in these shapes. So it's useful to have these boundaries because it actually reflects the boundaries of those counties, land and water area. But for thematic mapping, this is not the Michigan you'll want to show. It's not what people generally think of when they think of Michigan. They think of the land area. And so Tigris provides an alternative option to talk to a different data set that is provided by the US Census Bureau. And those are called the cartographic boundary shapefiles. All you have to do is specify the argument CB equals true. And that will pull in a cartographic boundary shapefile, which is clipped to the US shoreline. You can get even sort of lower resolution shapefiles that are really generalized and fast to map by specifying the resolution argument. By default, though, if you add the CB equals true argument, you're going to get a representation of Michigan that looks a lot more like what you would expect. So what I'm going to do is I'm going to go ahead and run that through. And Michigan looks a lot better. A couple other things to cover before we pause. Census tracts and block groups, and indeed sometimes even counties, change over time. Legal entities will rarely change shape because there is actually a legal process that needs to take place in order for, say, states and counties to change their boundaries. But statistical entities like census tracts and block groups and blocks are going to change with every decennial census. And we're talking about 2020 census data here, but in some cases, you're going to want to look at change over time. And Tigris provides access to data sets all the way back to 1990. So you can get data for a variety of different decennial census years and years in between. And so I live in Tarrant County, Texas, which is a pretty fast growing county in North Texas. And so what you can do here when you look at, say, census tracts, this is an issue that we're going to talk about a little bit more in next week's workshop with respect to harmonizing data across years, but it's just something to be aware of even when you're working with spatial data. So I can pull down data sets for Tarrant County for 1990, 2000, 2010, and 2020 using the code on this slide. I grab those data sets and if I click my environment tab, these are all the data sets that I've now loaded in. And take a look at this. In 1990, Tarrant County had 269 census tracts. By 2000, that was up to 310, then 357 by 2010. And then now for 2020, which is the boundaries that we're going to be using for the next 10 years, we're up to 449 census tracts. And so why does census redraw census tracts? Well, it's because they want to keep census tracts at approximately 4,000 people. That's going to obviously give or take. It's not going to be exactly 4,000 for all of them. But what this means is in a fast growing county like Tarrant County, which just went over 2 million people, in order for each census tract to have about 4,000 people, you need to redraw those tracts. And so we can visualize some of those differences here. I'm going to pop this out with the zoom so you can see a little bit better. You can see here that in 1990, there are far fewer tracts, especially up in the northeastern part of the county where there's been a lot of suburban growth. By 2020, a lot of those big census tracts in 1990 have been fully subdivided up into smaller census tracts. And so tracts certainly change over time, and that's something that's really important for analysts to be aware of. The last little bit that I want to show you is something that is really, really great, and really one of my favorite packages is the MapView R package. And for those of you coming from a GIS background, like I did, to R, one of the biggest limitations for the longest time in R was the inability to interactively view data. that is what GIS software like QGIS or ArcGIS is really great at. You load in your data set and you're immediately browsing around, you're clicking around and viewing your spatial data and sort of visually inspecting it. And R didn't really have functionality to do that until the map view package was invented a few years ago. The map view package is fantastic, and we'll be exploring some additional functionality of it later on in this workshop. But in brief, if you want to interactively browse your data in RStudio, I'm going to uncomment these lines of code. So all that means is I'm just going to delete those little number signs. And I will load the map view package and say map view my Tarrant 20 census tracts. And now I have an interactive, browsable view of all of those 449 census tracts in Tarrant County. I can zoom in here. I am sitting in this census tract right here at this moment. I can click and I get a pop-up that gives me all of the attribute information for that census tract. So looks like I'm sitting in census tract 1042.03 at the moment. So MapView is really fantastic for interactive browsing of spatial data, and it's had a lot of performance enhancements over the years, such that you can actually feed pretty large data sets to it, and it's going to handle it pretty well. If you want to sync up and interactively browse two data sets together, use the Leaf Sync package. I realize I didn't install that into my RStudio Cloud environment, so you won't have that pre-installed in yours, but I'm just going to go ahead and bypass that one for now. The last piece that I wanted to show you for this first portion of the workshop is how to pull national data sets. And I'll often get this question, you know, I'd like to do a national analysis of census tracts in the US. And so in this particular case, what we're working with here is typically census tracts are just distributed by state. And so you would need a more complex workflow to download all of those tracts by state and then assemble them. In the last couple of years, what the Census Bureau has done is something really exciting. And they've released national data sets for block groups and census tracts and a variety of other geographies. All you have to do now in Tigris, if you say, I want all of the census tracts in the United States, you just say tracts, you don't specify a state. You have to specify CB equals true. I'm going to run this through. I'm going to see if there are any memory issues. It looks like my memory is pretty strong. What I'm going to actually do is taking a look at my environment here. I'm going to click this little clear objects from workspace button. And I'm going to go ahead and clean up my environment to hopefully release a little bit of memory. And I'm going to go ahead and try downloading that entire US data set. Looks like I was able to get it. And I'm in a cloud environment, so it's going to download a little faster than it would if you're using, say, your home internet. But it literally took me a couple seconds to pull in all 85,188 census tracts for the United States. And now I have all the census tracts for 2020. And if I have an application that requires that, I was able to get it seamlessly and very quickly. So that's something I think that's pretty exciting, and something that really shows how Tigris, once you get the hang of working with GIS data in R, can really streamline your process of pulling down, in this case, a national census tract data set, which is typically pretty large and unwieldy to work with. All right, so this kind of concludes the first hour of the workshop. Just as a heads up, the way we're going to structure things for the workshop is typically I'm going to go about 50 minutes per hour, and then we're going to take about a 10-minute break and restart at the top of each hour, in which you'll have a little bit of time to stretch your legs. I have a little bit of time to stretch my legs, and I'm going to give you some exercises to work on. So you can practice a little bit, and if anything was a little too fast, you can go back through the code and try out some other things. So give this a try for yourself. That's your exercise. Take a look at the tigris documentation and explore all of the available geographies. So if we kind of go over to the documentation and scroll down, you'll see all those geographies that are available. These are all the functions that you can use. We've just scratched the surface. Try out one of them, see how they work, see if you can get it to work correctly. And then grab data for a state or a county of your choosing, and then try plotting the result with plot like you've learned, or try using map view and interactively browsing your data. So let's go ahead and pause there with the exercises. And then when we come back, it's going to be all about mapping the rest of the way out. So looking forward to starting that up. We'll start maybe just a minute or two after noon Eastern time.
All right, sounds great. Thanks, Kyle. So we'll be back in about 9 minutes. We'll start at about 2 after the hour. And if you have any questions, we've received a few questions already. Kyle has somehow managed to both present and catch some of those questions and answer them in real time. But if you have questions, please use the Q&A to submit those questions. We will try to respond to those when we come back. Thanks, everyone. All right, everyone, we are going to resume and get ready for the second hour of the session. But before we do, there were a couple questions we wanted to answer. And I see that there are a few good questions that have come in that I think will be applicable to a lot of people. Kyle, when you are available, if you let me know. Okay.
Yeah, I'm back.
Great. So the first question we have, is there a way to grab a geography like New York City? So New York City, for those who don't know, is comprised of 5 different counties. But is there a way to grab, say, 5 counties at once?
Yeah, there is. So you can't just go in and say, like, census tracts are organized by county in that census hierarchy. They're not organized by, say, place. I've seen a couple questions about that. So you'll grab tracts by county, and New York is distinct in that it has 5 counties inside of the city. But if you want more than one county, what you're going to do is basically request more than one county in your call to tracts. And so what I'm going to do is I'm going to open up this R script and library tigris. I could do something like NYC tracts is set to the tracts function, state equals New York, county equals, and to specify multiple elements in R at the same time, you use the C function, which combines multiple elements together. And so I would need the names of the counties, which are New York for Manhattan, Kings for Brooklyn, Queens for Queens, Bronx for the Bronx, and Richmond for Staten Island. I can pull that in. I get it near immediately. I can map view it. And here I have all my census tracts. This includes water area here, as you can see, but I have all my census tracts for New York City now. So that is how you do it.
Great. We also had another question about how to find the documentation for the package. I think you referenced right before the break, you referenced the documentation for the different geographic areas. Could you show where you found that?
Yeah, so 3 places to look. One is immediately within R, you can get the package documentation for any package pretty seamlessly. And so to do that, you'll click Packages, the Packages tab here, and then you'll search for the package you want. I'm going to type in tigris. I click there, and now I have all of the functions in the package. And I can go through and I can basically see the documentation for any of these different functions. Let's say I want to look at roads, and it'll tell me what I'm getting, how to use it, what the different arguments mean, and it'll link out to technical documentation. So that is a great way to look at what's available. There are also a couple other places that I'll go ahead and pop into the chat. One place, good place to look is in my book. And I will put that into the chat. If you go to chapter 5 of my book, which I'll link in the chat right now, you'll be able to read through a lot of the stuff that we're covering today. And so in that documentation, you'll get a lot of a sense of kind of what's going on, and specifically the data availability in tigris section will be of interest to many because it will tell you all of these different functions that are available. The third place would be the GitHub repository for tigris, but you're going to the book is probably going to be the best spot.
Great. There's one other thing that I just want to bring up that I think kind of connects to what Kyle said about the geography. So there was a question about the if you can get the cities, I think, within counties. And I don't have the slide immediately to show, but Kyle, do you have the slide that is in your slide deck that shows the kind of the hierarchy of the geographic areas?
Yes, let
just
me
to
go pull that up.
Point out that to be clear, a lot of the census geographies just don't fall within that main spine, that main backbone, that they don't properly nest within each other. So there are census tracts that go over place boundaries and vice versa. Same with block groups. They don't neatly nest within inside each other unless they fall kind of within, one of those sets of lines that go up and down from the nation down to census blocks. So as we saw, there are some cities that can be multiple counties. Cities don't necessarily have to be within one county either. So there's no clean way in which to just simply get all cities, say, within a county and vice versa.
Yeah, JP, your point is a really, really good one. And so if you need to get, say, there still will be use cases where you'll say, okay, I want all of the census tracts within this city. And, city boundaries can be very irregular and very strange looking. And so, in some cases like Houston, Texas, the city of Houston will control in many cases the roadways, but not the area around it. And so that's part of the city boundary, and the census tracts won't align with that very well. But if you do want to get, say, tracts or other geographies for a custom area, read through this section of my book. It's more advanced than we can cover today, as it requires spatial analysis and spatial overlay. But as you're sort of learning these concepts and learning how to do GIS tasks in R, and GIS tasks more generally, you'll be able to see how these different tools can be, flexibly used to subset information. So for example, this takes you through how to grab census tracts for the Kansas City metro area, which is a metro area that crosses state boundaries. So it's a slightly more complex use case, but it is very doable using the spatial data infrastructure in R. So that's something that if you're new to this stuff, maybe it's a goal where you can kind of get to and try it out. If you're familiar with this stuff already, read through this chapter 7, which is really an extension of a lot of the things that we're covering today.
All right, thanks. Why don't we go ahead and move on then to the second hour?
Yeah, sounds good. All right, so part 2, and this is probably what many of you showed up for today. It's all about mapping census data. We needed to spend that first part of the workshop delving into the data itself, because we need spatial data to make maps, and we need to understand spatial data before we make those maps. But now that we have an understanding of spatial data, let's go start making some maps. And a couple things about how we'll be acquiring data. We'll be acquiring data using the tidycensus R package. We covered tidycensus in detail last week, but I imagine that many of you did not attend last week's workshop. And so this might be your very first introduction. So a lot of the stuff that we will be talking about with respect to tidycensus simply can't go over all of that again, because then we wouldn't have time to get to the new content. But just for a brief overview, if you're brand new and just starting with this workshop, I want to show you how you can get up and running. If you need to, you can review the slides from last week to learn how to get set up with an API key and make some very basic data pulls. Additionally, something that you can do in the RStudio Cloud environment, if you grabbed the RStudio Cloud environment for today, if you click Files and then go back to the main project folder, you actually have all the materials from last week's workshop there already. if you click there and then bring up the code from last week's workshop, you're going to be taken through how to make basic data polls with tidycensus. And so it will be something where you'll have to kind of figure out some of it on your own, but just to illustrate a basic usage of tidycensus here, I can read in the tidycensus library, which is the package that I have authored to access data from the US Census Bureau. And then our core function is called getDecennial. And getDecennial is a function that accesses census data for the decennial US Census. And we're pulling here geography data at the state level for a specific variable. And if you want to know more about variable ID codes, look through the slides from last week. This is the variable from the 2020 census for total population. We specify year equals 2020. We can pull that down. We get a little message here about our census API key. And so that census API key, to boot that up again, is something that I've actually pre-included for you in the RStudio Cloud environment. And so if you go over here, this particular line of code that you'll uncomment will allow you to use a census API key that I have already set up. And so if I go in and I run this code, it's going to set a census API key in my R environment. And then I can go in and I can make data polls pretty seamlessly. So here's total population from the 2020 census. So that's a little bit of a crash course from last workshop. Of course, we want to start moving into the new stuff, but that is a way that you can get back up and running. Something that I am going to do, you'll notice in the free version of RStudio Cloud, and I'm going to paste that code right here. If you run this code that I've put into the chat, you're going to be able to use tidycensus just fine. So a couple things that I'm going to do, I'm going to clean up my environment right now. Because in the free version of RStudio Cloud, you only get so much memory. And if we're running through everything, we can exhaust that memory pretty quickly. So what I'm going to do is I'm going to clean up my console by clicking the Clear Console Broom button. I'm going to clean up my global environment by using the broom button here to remove objects from my workspace. And then I'm going to choose Session, and I'm just going to click Terminate R. That's going to reboot everything. And you'll notice that, don't worry about the unexpected crash, that's fine. You'll notice that I now have a lot more memory that I can work with. So this will get rid of all of your previous objects, just as a heads up, if you're in RStudio Cloud. It won't be an issue. You don't need to do this if you have R on your own computer. On your own computer, you should have ample memory for all this. It's just that for the free version of RStudio Cloud, you only get just a little bit of memory, because if you want more memory, you should sign up for a paid account. But we can use this for today. We're just going to clean up our environment. Again, to reiterate what I just did, I cleaned up my environment by clicking the Clear Objects from Workspace little broom icon. And then I did Session Terminate R, which is basically fully rebooting R, like fully rebooting my entire session. Now, this means that Tigris won't be loaded anymore. We would need to reload it, but it gives us enough memory. We're going to do this again after this hour of the workshop. So I'm going to go back to code.r and I'm going to navigate down to this section of the workshop, and we're going to go ahead and get started. So the typical process of mapping census data requires a lot of steps. Typically what you would have to do is first go and get the shapefiles from the census website, which we talked about in the first hour of this workshop. And then once you have those census shapefiles, you have to go to a separate website, pull down a CSV or Excel spreadsheet of your data, clean it up inside software like, say, a Microsoft Excel, and ultimately kind of you have that information now in potentially multiple software programs. So you have to find a software program that can accommodate both of those data formats, load in the spatial data, load in the tabular data, so that you have both of them and can work with them. Align key fields in your GIS. And what that means is you need to find something that you can match on. And oftentimes the columns that you're matching on will not be formatted the same way. Maybe one is formatted as text and the other is a number. So you need to do type conversion. Finally, once that's cleaned up, you merge your data together. And then you can actually start mapping your data. I've taught GIS for 10 plus years at the university level, and this is often really hard for students. It is very laborious. It involves working with multiple software packages. It involves multiple steps and just combing through this data. And frankly, it was something I used to do all the time, and it was a headache. And I didn't really want to do it anymore. And I started to learn R, and I thought, is there an easier way to do this? Because this is something that is very repetitive. It is important, and we're dealing with different data each time, but it is basically the same process over and over and over again. Can this be better? And that was a major motivation for writing tidycensus. Tidycensus is an R package, again, that communicates with the US Census Bureau's Application Programming Interface, or API, to pull in demographic data at custom geographies for many, many variables in the Decennial US Census and other data sets that we'll be covering next week. Instead of going through the process that I just described on the last slide, what tidycensus includes is an argument called geometry equals true. And what geometry equals true does is that entire process for you. It identifies for the location for which you're pulling demographic data, what the appropriate shapes are. It merges those shapes internally to your demographic data. It formats everything appropriately for you, and it gives you back spatial data enriched with demographic data by adding one extra line of code. This is the main reason I wrote tidycensus, and I use this feature constantly. So let me show you how this works. So we go over here, we're going to load in the tidycensus library with library tidycensus, and we're going to set the option tigris use cache equals true, because I'm going to show you how the shapefile caching works. We're going to set our census API key because I just cleaned out my entire environment, and then we're going to run this bit of code. All right, and so basically in just a second, I've been able to do this entire process of downloading all of the data from disparate sources, assembling the data, merging it, and giving me back an enriched geographic data set that, as you'll see here, includes a census ID code and a name for each county in Texas, the census variable, which is the variable for total population, the value for total population for 2020, and then our familiar geometry column. That's all been assembled for us in a second. And this is a process that takes my GIS students manually hours upon hours to do. And so once you've been able to accomplish this, you can get to mapping your data so much faster, because the overhead of acquiring and processing your data is already handled for you. And so I can plot my data and visualize my data in a variety of different ways. And so we've learned how to use the plot method to plot geometries. And so I could do the same thing if I did something like plot tx underscore population. And I can see the geometries that are associated. And I do see kind of one message coming through in the chat, seeing an error message, no applicable method for gather. Make sure that you have all updated packages installed. So packages fully updated, that frequently comes up if you have an old version of tidycensus installed. And so in this particular case, or one other potential reason it would come up is not putting in year equals 2020 and trying to pull a 2020 variable from, say, the 2010 census. So we can map out our geometries here if we want to, or we can specify a specific column that we want to map and visualize that accordingly. And so if we specify that column, it'll actually map out in a color-coded map the population column, which in this case is the value. And frankly, it's not a perfect map by any means. It's just an underlying visualization of the data. But what we see here is Harris County, Texas, which is Houston, has the biggest population. That's the bright yellow. The DFW metro area, here we have San Antonio, Austin area. Those tend to be the brighter colors because those are the larger geographies by population. There are a lot of other ways that we can map out census data, and a very popular package available for visualization, which we covered extensively in last week's workshop, is ggplot2. And ggplot2 can make maps of simple features objects pretty seamlessly. So if you remember from last week, if you're able to attend, ggplot2 requires a data set and an aesthetic passed to this ggplot function. And what that'll do then is that information is then passed to a geom function that tells ggplot2 how to draw shapes. And it could be bars, it could be dots, or if you have geometry information, you can use geom_sf to make an appropriate map very, very quickly. And so if I go back to R here, I can load in, I'm going to load in the tidyverse, which we'll be using to get access to all of the different data wrangling tools that work well with tidycensus. As you can see here, now I've created a plot that is similar in spirit to the one that uses base R plotting, but uses ggplot2 styles. And so that really highlights, again, those large counties in Texas, such as in Houston and Dallas-Fort Worth area. So these are basic, they are maps. We've made our first maps, but they're not really great maps, in part because, for one, mapping out a count value like total population at the county level for a state like Texas that has 254 counties, in which the counties literally range from over 4 million over here in Harris County to, I believe, 67 people in this highlighted county here, which is Loving County. The scale is massive, and so showing variations is somewhat difficult. And so we're going to take a look at some different map types and some different ways of representing data, particularly at the neighborhood level, because that often is what gets really interesting to visualize. And so I'm going to walk you through a number of examples using a different package that is really tailor-made for making thematic maps, and that's tmap. So tmap is a comprehensive package for thematic mapping in R. It is voluminous in the number of features that are available to you, and we're only going to scratch the surface today. It has a ggplot2-like syntax where you initialize a map and then you sort of layer on different elements of the map. So it's familiar to ggplot2 users. It'll also feel familiar to GIS users because a lot of the defaults are similar to defaults in GIS software, and a lot of the terminology is similar to some of the terminology in GIS software. So, I've found that if people often say, well, I'm coming from ArcGIS background and I want to make maps in R. How do I do this sort of thing? And in many cases, data visualization software in R speaks the language of data visualization and not necessarily cartography. And so tmap really comes from a cartography perspective, which makes it pretty intuitive if you're coming from the GIS world. It's also pretty intuitive for beginners as well because of the way that things are named. And I'm going to illustrate that in just a little bit. For a little bit of basic vocabulary for those of you who are new to mapping, thematic mapping refers to mapping that's not designed to get you from point A to point B, but rather mapping that is designed to show some characteristic of an underlying data set, a theme, if you will. So a reference map is going to be a map where you'll pull up Google Maps and it'll have, oh, here are all the restaurants and here are the roads and here are the parks. It's designed as a general reference. If you have those old AAA maps as well, that's a reference map. A thematic map is not that. A thematic map focuses on one or two specific characteristics of your data and then uses a map, uses a spatial representation of your data to show variation in that characteristic. And so for mapping census data, we are creating thematic maps. That is what we're doing. So let's go ahead and pull down some data that is going to be familiar if you attended last week's workshop. It's a touch more sophisticated if you are new. So I am going to step through exactly what it's doing. Our job, and of course I catch my first typo. I was originally doing Cook County and then I switched to Hennepin County, Minnesota. So please ignore. What we're going to be pulling down is racial and ethnic geography for Hennepin County, Minnesota. And so I'm going to go ahead and run through this code and we're going to take a look at what it's doing, and I'll explain to you all of kind of the elements of what's going on here. So I get my data very, very quickly. What we've been doing typically is typing out the name of the object. I'm going to type Hennepin race and printing that out. So this is one such way of looking at your data. The glimpse function in the dplyr package is also really nice. It provides a different view of looking at your data. So it's really kind of up to you how you want to take a peek at it, but both ways end up being very reasonable. So what do we have here? I'm going to step you through exactly what we just did. So we created a new object called Hennepin race that is for race and ethnicity by group in Hennepin County, Minnesota. We use the get decennial function to pull data from the decennial US Census. And then we specify a series of arguments to tell R specifically how the data should come back. We say geography equals tract because we want data at the census tract level. We want data for the state of Minnesota in Hennepin County, which is Minneapolis and its western suburbs. For variables, we talked about how to use C to pull in multiple counties. You can do that for variables from the Census Bureau as well. Up here, we specified one character string for a single census variable. If you want multiple variables, you specify multiples. And so here we have Hispanic, white, Black, Native for Native American or Alaska Native, and Asian. And we use something called a named vector, where instead of saying just variables equals census code, we specify how we want those census codes to be replaced in the output data set. And so instead of using the code for Hispanic, which will be used to acquire data, we're going to replace that in the output data set with the custom name Hispanic. We also specify a summary variable, which is used in tidycensus. We covered this last week, but if you're new, a summary variable can be specified to add a second column summary value to be used as a denominator for calculation of rates, proportions, and percentages. So in this particular case, what we get back is the census ID, the name of the place, and then for each of those locations, we get 5 groups: Hispanic, white, Black, Native, and Asian. We get the value for that group and the summary value for that group, which is total population. We then use the tidyverse mutate function to calculate a percentage, which is going to be pretty important for some of the map types that we're going to be creating. So now, and this is partly why I use dplyr glimpse to take a look at it, because you can see it more clearly. For each group, for each census tract, we have not only an we not only have a count from the census, but we also have a percent of total value. All right, so let's start making some maps. TMAP can do basic plotting, much like base R and much like ggplot2. And so what we're going to do, as our data are in long form, so each census tract is represented 5 times, once for each group, we are going to jump back here, use the filter function from the tidyverse to just extract out one of those groups and focus in on the non-Hispanic Black population by census tract in Hennepin County for 2020. So if I specify for a given data set that I want to make a basic plot, I initialize my map with the tm shape command. And I say, let's initialize a map using the shapes in this Hennepin Black object. I then, with the plus sign, layer on map elements. And so if I specify tm_polygons, it plots polygons for each census tract using the geometry information that we have in there. So I'm going to go ahead and run that through. TMAP takes a few moments to load as it's a very large package. And so here we have all of the census tracts in Hennepin County, Minnesota. We're going to keep making this a little bit more complex as we go. To make something called a choropleth map, which is a nomenclature that refers to a map that shows statistical variation through color or shading of areas. So maybe darker areas will reflect a greater concentration of something. Lighter areas will reflect a lower concentration of something. That's what choropleth maps do. Choropleth maps almost exclusively should be used with normalized data such as rates or percentages, not counts, because of 2 things. One is, if you're using rates, if you're using counts, you'll in many cases inappropriately attribute a greater concentration to locations that have basically larger baseline populations. And this is particularly true. It's less of an issue with census tracts. It's more of an issue when you have vastly kind of varying underlying populations, like say counties in the state of Texas. And additionally, it's a way of sort of muting out and sort of correcting for the influence of diverging sizes of shapes. And so we're going to use our percent column, and we're basically going to say draw polygons with the column equals percent. Let's go ahead and take a look at our first choropleth map. It's not great yet. We have some overlapping issues with where the legend was plotted, but we can see in general terms how it works though. We have the darker areas that are representing a greater concentration and the lighter areas that are representing a lower concentration. The default color palette here, for those of you who used ArcMap back in the day, this is the default color palette for choropleth maps. And so TMAP does implement that by default. So it's a start, but it's still not very satisfactory. We might be interested in customizing a variety of different things, maybe different colors, move the legend out of the way. We might want different class intervals. So what TMAP defaults to is what it calls pretty breaks for 5 classes. And so it looks at the distribution and then it will divide it up into sort of evenly spaced breaks. In this case, it's 0 to 20%, 20 to 40%, 40 to 60%. In some cases, this kind of understates the distribution because in Hennepin County, the Black population is heavily concentrated in a couple areas. And so what this does is, even though there are census tracts with variation in their Black populations in the suburban parts of Hennepin County, out where my cursor is, you can't see it with this default visualization scheme. So we can make modifications. You can change color palettes with the palette parameter If you're familiar with Color Brewer or Veritas color palettes, you can grab any of those. If you've mapped with GIS software before, the style parameter implements various breaks methods. You can use equal intervals. You can use quantiles where you have an equal number of observations in each bucket, or you can use the natural breaks Jenks algorithm, which looks for sort of naturally occurring divides in your data. And so in this particular case, we're making some modifications. We're saying we want the column to map to be %. We're going to change the style, however, to quantile, which means we're going to put the same number of census tracts into each bucket. We're going to change the palette to purples. We're going to set a title for our legend. And then we're going to add on this TM layout function that says that we want a plot title. We're going to remove the frame around our census tracts. And then importantly, we specify the argument legend.outside equals true to move the legend off of our data and over to the side. We can run this through and we get a much cleaner looking map that appropriately shows variations in the suburbs that weren't being shown before, divides up our data into 7 classes, gives us some informative kind of context with respect to the legend, and overall is just a superior presentation. So we can keep modifying this. If you have the TMap tools package installed, which may not be installed in our Studio Cloud, but actually I'll show you briefly how you can install any packages. If you're in our Studio Cloud and you want to install a new package, something that you can do, like let's say we want the TMap tools package. What we'll do is we can type in install.packages, that function. I can type in TMap tools. I hit enter. It'll tell me one or more of the packages to be updated or currently loaded. Do you want to restart R prior to installing? I'll click yes. This will restart my R session and it will pull in the TMap tools package. Now, granted, what this does is sort of refreshes my environment. So I would need to go back if I just did this and reload in my packages such as tidycensus, tidyverse, and TMap. So that's just if you're new to R and you hear, oh, I need to install a package. How do I do that? That's how you would take care of that. The command TMap tools palette explorer allows you to interactively browse data. And so if I hit that, looks like I need the shiny package as well. Just take a moment to pull all that in. And install shiny.js as well. You might not want to go through this whole process, but this is useful context for those of you who are new to R. If you ever get the message, oh, it doesn't work, there is no package called, try installing it with install.packages. Now I'll pull up my palette explorer. And what we'll see here is this really cool color palette explorer where you can go through and see all of these different names of palettes that are available in TMap. And so moving through, I see a question about the palette explorer. This command in the slides, it's the palette explorer command in TMap tools. If you run this code from the slides, TMap tools : palette explorer, and you make sure that you have all the underlying packages installed. So you'll need the shiny package and you'll need the shiny.js package. It's pretty cool. There are a variety of other options that you can specify. So I'm going to change the style to natural breaks Jenks. I can even do legend.hist equals true to draw a little distribution histogram. I'm changing the color palette to Viridis. I picked a new palette from my palette explorer. And I go ahead and run that through. And something I'd probably want to do is make additional modifications just to show you the help documentation for some of these functions. If I want to bring up the help documentation for any function, like TM layout, I can use the question mark sign and then type in the name of the function. And that's going to pull up that documentation. There are so many options that you can specify. It is voluminous, fonts, font sizes, positioning, margins, background colors. There's way more than I have time to cover in this workshop. I encourage you to read through and try modifying some of these options. I want to show you briefly a couple of other cartographic types before we move into our second break. Because choropleth maps are great, but there are a couple things that they're pretty bad at. One is, well, let me give kind of three drawbacks. One drawback is they're not good for count data for the reasons I talked about. And in some cases, you want to map counts. You don't necessarily, let's say you have a situation where you want to show where the Black population is located in Hennepin County, and maybe for some reason you have a geographic unit with 10 people in it, and 5 of those people identified as Black on the census. And it'll show as 50% Black, which is a lot, but it's only 5 people. And this ends up being a major issue because you're showing a significant concentration of something that is fairly arbitrary for a very small population. So that's one thing. Another thing is that choropleth maps are bad at showing internal heterogeneity of units. Like I can show the concentration of the Black population, but I can't really show the concentration of other populations very well because we're just focusing on one color at a time. And another thing is that colors can be very difficult for people to perceive. You have color blindness in the population that needs to be accounted for. Now, Viridis is a colorblind safe palette that we're using here, but nonetheless, perceiving differences among colors tends to be reasonably difficult for people to do. So let's talk about a few other map types. For count data, graduated symbol maps are pretty good. What they'll do is they'll draw different size symbols that are proportional to a value in a data set. And they don't have to be exclusively used for count data, but they are appropriate for count data. And the TM bubbles function will draw a graduated symbol map. And so what I'm doing here is I'm specifying for the Black population in Hennepin County, draw the polygons, but without a polygon fill. That'll be our background. And then draw bubbles on top of it. And I'm setting alpha equals 0.5 to make them semi-transparent. If I run that through, I get a bubble map that appropriately now is showing the concentration. I'm probably overplotting a bit, so I may want to modify the underlying size of my bubbles. There is an argument in TM bubbles that allows you to set the scale of the bubbles. So if you want to make them proportionally larger or proportionally smaller, you can do that. But graduated symbol maps are a nice alternative to choropleth maps in this particular case. You can also use something called a faceted map or a small multiples map that actually plots different maps by group side by side in a grid so that you can rapidly make comparisons. And so in this particular case, I mentioned that internal heterogeneity of locations is very hard to represent on a choropleth map. A workaround is to show multiple choropleth maps side by side, one for each group. And so I use the TM facets function to specify that. And I'm saying here, if we go back to our original data, we note that in the Hennepin race data set, we have for each census tract 5 groups. And those groups are identified in the variable column. So we're going to use that variable column for faceting. If I run that facet map, I'm basically saying, make me a separate map by variable. I want that map to be a choropleth map using the blues palette. I'm going to move the legend to try to fill up the missing facet. It'll show up slightly differently depending on your specific computer configuration. So mine, I'm going to want to move that down a little bit, and you'll modify the position, say with the legend position. So I can move this down a little bit more if I want to by changing that legend position. So that moves it up a little bit. I could maybe set this and try to 0. And that moves it down to fill that up. So we're basically kind of thinking about relative horizontal and vertical positioning of the legend element. And so this sometimes takes a little bit of trial and error, as you can see, to find the right spot, depending on how your monitor and how your system is set up. But as you can see, there's a lot of configuration that you can do. So I've moved the legend from basically over here to fill up this empty panel. And now I can make comparisons across the different groups. So you can see in Hennepin County, there are areas where you see a larger Black concentration. Hennepin County is a fairly white county. So this white choropleth map isn't that interesting given the consistent color scale, but it allows us to compare the groups side by side. The last map type that I want to show you before we get into some discussion of map elements, this is something that will work in our Studio Cloud. It is a brand new feature that I just created this week. So if you have the officially installed version of tidycensus from install.packages tidycensus, this isn't going to work. This is a brand new feature. You can install the development version of tidycensus using the command remotes : install _github Walker KE tidycensus. There may be some debugging depending on your system if you do try this. So I'm not going to walk through that process right now. If you are in our Studio Cloud, you have the development version of tidycensus with the brand new feature for dot density mapping that I created this week. And this is really the first time that I'm showing it to anybody how this works. So I wrote this function as dot density because I was thinking for this workshop, I want to show dot density maps, but the problem is it's typically really slow to do that. Is there a fast way to do it? And what as dot density does, it creates something called a dot density map where dots are scattered within polygons proportional to different data values for different groups and then shuffled to show internal heterogeneity. And so what we're going to create here with the as dot density function is for the population of each group, draw a single dot randomly positioned within each census tract for every 250 members of each racial or ethnic group. What we're going to do then is use this tm dots function to draw tiny little dots. So we're basically converting our polygons to a bunch of scattered points within those polygons. And so we can run that through, and what we're going to get is a map that looks like this. And traditionally, this is something that has been fairly laborious to create. You'll see how fast this goes. We generate the dots, we plot the dots, we take a look at the dot map, and there you go. We have a dot density map within seconds. This is something that used to take several minutes using sort of older approaches. So I'm really excited about this. The dots are scattered correctly, so we don't have overlapping groups. But as you can see here, what we're showing now is internal heterogeneity. So the northwest side of Minneapolis, called Minneapolis's north side, you see it's predominantly Black for the blue dots with some Asian populations and white populations scattered in. the near south side of Minneapolis, predominantly Black and Hispanic. The southwest portion of Minneapolis, you see here, almost exclusively white, as is the outlying part of Hennepin County. The northern suburbs of Minneapolis, pretty racially mixed, and you have racial mixing as well in the southern suburbs. So dot density maps are great for showing internal heterogeneity. One drawback is you'll often have people who are viewing these maps and they don't know how to interpret them. And so they'll say, is each dot a person? Well, are you saying that, but there's a city right here and you put the dots over here? You know, that doesn't make sense to me. So I'll show you a potential resolution to this in the third hour of the workshop, but that's just something to be aware of if you're using this. A couple other things that I want to show before we pause for the break. Something that cartographers will common do in a GIS context is add cartographic elements. And so cartographic elements are going to be extra features of a map that add additional reference. So it's not going to be the focus of your map. Your data is going to be your focus, but it puts your data into context. And so a common thing that you're going to do is plot a base map. And for me, the easiest way to get a base map for your TMAP maps is to use the ROSM package. And so what that does is it pulls in for a given location. And as a heads up, you'll have to do an extra little line library SF to get this to work. But if we pull in the ROSM and the SF package, what we can do is use this osm.raster function to kind of detect the area around Hennepin County and then pull in map tiles. We're using Carto's really nicely rendered OpenStreetMap map tiles as a base map. And then I can plot that using the TM-RGB function. And this is what our underlying base map is going to look like. We can then take that information and use it as an underlying layer on top of which we can plot our census shapes. And we can pick which census shapes we want to do. What I'm going to do here is on top of that base map, I'm going to recreate that choropleth map of the Black population share by census tract that we already created. And so if I run through this next bit of code, you'll notice that I now plot my shapes on top of it. And so if you're familiar with Hennepin County, Minnesota, you already knew the places I was talking about. If you're not familiar with it, you might not know where these places are. And so now we can see up here, these are the suburbs of Brooklyn Park and Brooklyn Center. Here's where the city of Minneapolis is. And you can see some of these outlying areas like Rogers, Medina, and so on and so forth, shown under our semi-transparent polygons, as I specified in alpha of 0.6. A couple more things before we break. You might also be interested in adding ancillary map elements. This is something you'll commonly do in a GIS, such as a north arrow, maybe some descriptive text. Julia's note, this is something that I just neglected to put in the code. To get the STB box, you need to specify library SF. That will make it work. If you do library SF, then that will work. So to add cartographic elements, I told you TMAP has so many options. TM scale bar adds a scale bar. TM compass adds a compass, and you can specify the positioning. TM credits adds a little caption to your map. I can run that through. And now I have a caption. I probably need to modify based on my configuration here, the font size and the spacing, but this is part of cartography. You're always tweaking and modifying once you have those elements in place. The last piece, and then let's break, you might say, this is great, TMAP seems cool, but I still really like using ArcGIS. Can I get my data from R and then just use ArcGIS to make my maps instead? Of course you can. If you use in the SF package, the STWrite function, you can write any R spatial object to a spatial data set of your choice. So commonly you'll be using a shapefile. Maybe you're interested in using GeoPackage or GeoJSON, but this is all you need to do to write out your data set to a shapefile. Let's say I have a subdirectory called data. I'm not saying don't run this code right now. You can if you want to try it. It presumes a subdirectory called data where I would tend to store my data. And what that'll do is it'll write it out to a shapefile, which you can go ahead and just load straight into ArcGIS and make your map over there, because there's some benefits to cartography in ArcGIS. TMap is wonderful. I like it a lot. There is something to be said to be able to click and drag around specific map elements when doing very custom cartography. And so if that is what you'd like to do, then a lot of people use tidycensus this way. They acquire the data on the R side, they process the data on the R side, and then they take that data out to QGIS or ArcGIS and make their maps over there. All right, so that concludes this session. Let's take a little bit of a break and try making your own map with TMap. So if you're just getting started for today, take the Hennepin County code and try a different state and a different county, and try just reproducing everything with a different state county combination. If you're more comfortable with tidycensus at this stage, try a different variable and make a map of a different variable and a different location. So let's take a few moments to pause. Why don't we come back at about, let's say 1:05 and start with part 3 of the workshop.
Great, thanks, Kyle. Everyone, so we have about 7 minutes before we resume the final segment of this session. 5 after, thanks. All right, we are at about 5 after. We'll get started in just a moment.
Yeah, sounds good, JP.
Great. Okay. So we had a couple questions come in during the last session. And one thing that came up, and I know I sometimes get this question, when you have a map, or sorry, when you're working, yes, when you have a map and you have a legend, and you see that a category both begins on one number and the next category, or sorry, ends on one number and the next category begins on that number. So say if the state of Michigan happens to fall right on that breakpoint between two different categories and say a percentage, does it end up in both categories or does it end up in just one or the other? How does that happen?
No, it'll only be in the one. Likely you'll see that on the legend because of rounding. And so you can think of it as, this particular class, includes everything here. And ultimately, if you're right on the border, you're not going to end up in both categories. Something that you can do is get some more control over your categories as well. And this is something you can typically interpret these, and I think I would need to double check on this, but I believe it's interpreted as everything up until, but not including this value. And then it's basically everything from like 0 to basically 2.41999 repeating. And then we start here, and then we start here, and then we go up to the maximum value. I think that's how TMAP does it. It's possible it's the other way, but it's I would need to double check that. But it's not going to put, these two numbers don't mean the same thing. It just shows that because of rounding. That said, one thing that you can do in TMAP, if I look at the help documentation for TM polygons, you can specify specific breaks in your data. This gets calculated for you typically, but if you actually want to put in manual breakpoints based on what makes sense for your specific data, you can do that. And then you can have a little bit more control over what's going in. So that's a handy option in TMAP.
Great. Well, we're talking about TMAP and some of the settings with it. There was a question about whether when creating a bubble map, if there's the ability to change the feature boundary thickness.
Yeah, absolutely. So if you look through here in TM polygons, you'll see that you can specify a color, an alpha, a border color, and a border alpha. What that means is that I can actually modify basically any particular element of my data. And with the borders as well, you can modify with using this LWD parameter, you can modify the width. And so if we look at our bubble map, by default, that's what our polygons look like. Maybe I want to make the background a lot more muted. I could change the color to white, and I could change the LWD equals 0.2. And let's just see how that changes it. Now you can see it's a lot more muted. I've made my boundaries, my polygon boundaries, a lot more muted, and I've made the background white, really bringing my bubbles to the forefront. So you can customize each element in turn like that.
All right, great. Why don't we go ahead and move on to the final session in this workshop. We have, it looks like about 50 minutes left, so I want to give as much time to you, to people to talk about the content as possible. So we'll go ahead and move on. Go ahead, Kyle, take it away.
Yeah, sounds good. All right, so You notice up here, my RAM is kind of way up at the beginning. I'm gonna try to take that through as far as I can until R tells me that I'm out of space. And then we'll kind of refresh if and when needed, because we are gonna do a couple things that are a little bit more computationally intensive. But I wanna keep my environment, at least for the first portion, because I'm gonna be reusing some of this Hennepin County information. So for the third part of the workshop, we're covering some more advanced use cases. And the two advanced use cases we're going to be covering are interactive mapping and advanced geometry handling. I'll explain what advanced geometry handling means in just a moment. Interactive mapping is a bit more self-explanatory. And one thing that is fantastic about TMAP is to create an interactive map or to create a static map like we've been doing. It's the same code. All you have to do is just change the viewing mode. And so the default viewing mode in TMAP is tmap_mode view. That by default creates an interactive map. Excuse me, tmap_mode plot creates a static map. That's the default. If you change that to tmap mode view, it creates an interactive map by default. And so I can go in and specify my same plotting code that I used before. But if I set tmap mode view first and then rerun it, now I have an interactive browsable map where I can zoom in, zoom out. I can change the base map if I want to. You'll note that I set the alpha to 0.6, which I didn't do before. That makes my layer semi-transparent. So I can see here's Minneapolis. Let me zoom in here to the northern suburbs. I can click on any location and I get a little pop-up that shows me the percentage value that I'm mapping. So making interactive maps in R, very, very quick. If I want to, I can customize the options as well. So if I specify in TMAP options, the base maps that I want, I can use a variety of sort of different base map names to bring in some different base maps. And if you look at the help documentation for TMAP options, there'll be some cues on how to specify those names and what's available. There are quite a few that are available. I can change the ID to basically change the title of the pop-up for each location. So if I don't want the census geo ID, which it's defaulting to, and I want the census tract name instead, I can just specify that as the ID instead. And making these modifications brings up the same interactive map, but now I'm using Esri's default map tiles, or I can change to the popular stem and toner tiles, which are really nice. Or I picked a dark map. So if I want a dark base map, I have that too. And now you'll notice when I hover over every tract, it gives me the name of the tract, and I click, I get the name of the tract as well instead of the census GeoID. See, a follow-up question, can you use TMAP to implement interactive maps into Shiny apps? You absolutely can. I'm not going to cover that today, but you absolutely can do that. TMAP has methods for working with their interactives inside of a Shiny environment. And Shiny, for those of you who are new to R, is a data dashboarding platform within R. And it basically allows you to create interactive web applications using R code. It's really, really cool. I have a basic example of it at the end of chapter 6 of my book, if you'd like to take a look. But it's beyond the scope of what we're covering today. But if you're starting to get more comfortable with R, it is one of the most useful packages that you'll encounter. When you're working with interactive maps, you might be interested in saving out your map to an HTML file that you can then embed in your website and or share with someone else. Use the tmap save function to do this. What you would do is you would assign your interactive map to a variable, which I haven't done here. I'm just hypothetically saying for an arbitrary tmap object named tmap obj, save it to an HTML file. That's all you have to do. It'll write it out to a standalone HTML file that you can go ahead and email to someone or post on your website. And the great thing about TMAP Save, it actually can save out static plots too. You can just write it to a JPEG or a PNG graphic, and then you'll have a static map that you can plug into your reports or slideshows or whatever it is that you're working on. The map, if you want a really quick interactive map, you sometimes are going to want to use the map view package for that. I showed you how to use map view to interactively basically browse spatial objects from Tigris really quickly. If you specify a column to the zcall parameter, so basically say zcall equals something, it'll make an interactive choropleth map for browsing straight out of the box. And this is extraordinarily useful. I'm going to go ahead and run that through. And it's like I killed my environment before. I'm going to need to do a library map view to do that. And now, with a single line of code, I have an interactive, browsable choropleth map that allows me to really quickly explore variations. And MapView has a number of functions that allow you to customize this output and actually do some cartography for it. I typically say when I'm working with census data, I just want to know at the very beginning, what is a basic distribution before I really start to do any other work with it. I'll use MapView for that. I'll say MapView, specify a zcall, show me what's going on. I'm going to go explore. And that is really a great first way to start exploring your data graphically. All right, so that is just a little primer about creating interactive maps in R. There's a whole lot more that you can do with it. These maps are built on the Leaflet package, which wraps the Leaflet JavaScript library for interactive mapping, which is probably the most popular interactive mapping library in the world. And the Leaflet package integrates really well with Shiny for data dashboards and interactive web applications. And just a quick acknowledgement of the creator of the Leaflet package. Anytime you're making an interactive map in R, you're using the Leaflet package, which was created by Vladimir Agafonkin, who is currently having a very difficult time in Ukraine with his family right now. He's based out of Kiev. So anytime you're using Leaflet, give some thought to his situation and his family, because he was the one that created the software that we're all using to make interactive maps every day. Those packages are wonderful and fantastic and really allow you to create rich interactive applications that ultimately can be built into really any sort of use case that you can think of. So I encourage you to check that out. Moving into really kind of the next section, I'm going to go through some advanced use cases. So we've gotten our feet wet with spatial data. We've gotten our feet wet with cartography using TMAP. We have a sense of how to do some more advanced things, and we've learned how to make some interactive maps fairly quickly. And so as you get more comfortable with R, as you get more comfortable with spatial data, you're going to want to do more customization that allows for better representation of information, allows for more sophisticated visualization. And I want to give you a preview of a few different ways that you can accomplish that. And so not all of this is incredibly beginner friendly. And we're going to have to gloss over some more advanced topics, but I want to give you a sense of where you can go, and then refer you certainly to my book to delve in deeper and work through this in a self-paced sense. So let's get started with a few different use cases. I frequently get questions about mapping population density. in a comparative context. And tidycensus by default, there isn't a population density variable in the decennial census that you can just pull down. So you have to figure out a way to calculate it yourself. And this isn't something that is straightforward because we get demographic data, say from the census, but population density requires both demographic data and some information about land area so we can actually calculate population density. There is functionality, however, in tidycensus that facilitates this, and it uses an option that not a lot of people know about. There's an argument in tidycensus called keep geovars that is by default set to false. So what tidycensus does when it grabs geometry for an object is it calls tigris internally, uses the appropriate tigris function, and it attaches that geometry to your demographic data and then gets rid of all those other columns that we looked at that come through from tigris by default. You can keep all those columns if you want by setting the option keep geovars equals true. This will retain all of the original columns from the census shapefile, which includes a column called a land for land area. We can then calculate population density by dividing our population value by the land area. And so a land comes in square meters by default. And so we can multiply that by 1,000,000 to get square kilometers. And if we run this code through for the state of Michigan, we can, I realize here, this was a late breaking. I thought I'm going to put something in on population density. I'm going to put it in this morning. And I didn't transfer it over to this script. So this code is something that we need. If you want to follow along here, you can copy paste it over from the slides if you have the deck up. But my apologies. I thought I really want to put in population density. And so it looks like Matthew posted in that code into the chat, which I very much appreciate. So kind of late breaking decisions, but it didn't make it into this script. And so I'm going to run that through. I'm going to set my tmap mode to plotting because I'm going to go back to a static map. And I'm going to pull in that population density information. And now I have a data set that has population density calculated. I can create a map of this data using the same mapping code that you've already learned. One thing that I'm going to modify very briefly, and this will be familiar to those of you who come from a GIS background, less familiar for new users. I mentioned at the very beginning of the workshop that census data by default are stored in a coordinate reference system called NAD83, or North American Datum of 1983, which is what's called a geographic coordinate system where coordinates are referenced to a three-dimensional model of the Earth's surface using longitude and latitude. It's a lot of vocabulary. Coordinate reference systems are frameworks that reference locations in your data to actual locations on the Earth's surface. And we need to make distortions and modifications to do this because in many cases we are mapping data in 2 dimensions, but that data is actually 3-dimensional because the Earth is 3-dimensional. And so in many cases, we'll want to modify the coordinate reference system of our data to minimize distortion introduced from that sort of 3D to 2D transformation when making maps. This is a topic that you do weeks on in a GIS course. It is not something we can truly adequately cover in a workshop today, but I want to give at least a brief overview. Typically, when you're mapping data, it's useful to use a projected coordinate reference system. And it's not always easy to figure out exactly how to find one. So I wrote a package called CRS Suggest to facilitate this process. It basically takes in an input spatial data set. It identifies some potential coordinate reference systems that would be suitable for that location and gives you back codes that you can use to modify your data. And I'll show you how to do that a little bit later. Or you can use it directly in tmap with this projection argument to specify a code for a location and represent your data with a minimal amount of distortion. And so the way that CRS suggest works is I'm going to load it in, and I'm going to grab some suggested coordinate reference systems for Michigan. And one really cool trick I just learned last week in our studio, if you control click on any object that already exists, it'll pop up that object for viewing interactively in our studio. This sort of blew my mind that you can do this. So I just learned about it last week. If you have an object in your script that is already defined, control click on the code and it'll just pop it up for you to take a look at. And so it looks like for Michigan, the statewide coordinate system is called Michigan Oblique Mercator. And it comes in a variety of different flavors. But generally speaking, the newest projection is the one that is found at the top. So we can go ahead and we can grab that CRS code, and this will be a coordinate system that's appropriate for mapping the entire state of Michigan. If we go back to our code, then we can create a population density map in a coordinate system that minimizes distortion. We can run that through. And so here I now have a population density map expressed as people per square kilometer by county for the state of Michigan. Predictably, you have higher densities in and around Detroit and lower densities in other parts of the state. So for local areas, coordinate reference systems, you can usually find one that works. What about making national maps? National maps are hard for the United States because we have different territories and states that are in vastly disparate locations. So mapping the continental United States is one thing. What if we're trying to map Alaska, Hawaii, and Puerto Rico along with the continental United States all together? That's really tough. And using the code that you've learned by default isn't going to work very well. So let's go in and grab some data. And let's say we want to make a national map for the US plus DC and Puerto Rico for the percent Hispanic population. So we have our Hispanic variable, we have our total population variable, we calculate a percentage, and we pull that data down. It'll just take a moment to grab. And now let's try to make a national map of that data using the TMAP code that we have learned. So we're making a few modifications. I'm using a continuous color palette with style equals cont. We remember that LWD argument. I'm making the polygon boundaries very, very narrow. So let's see what this looks like. We're plotting thousands of counties, so it'll just take a moment to render. Appears to me, I was wondering at some point if my R session was going to crash. So we're using the free version of our Studio Cloud. I thought this was going to happen at one point. It just happened. And so that's actually fine because it's cleared out my memory. So we're just going to go ahead and rerun this starting right here. I'm going to do library tidycensus, library tmap. Let's see if I need to set the API key. I might need to. We're going to need library tidyverse. So if your session just crashed as mine did, because you're using our Studio Cloud, we're just going to repopulate those different libraries and rebuild our environment. So I'm going to go back up here. I'm going to grab my census API key. And so kind of where you're going to want to go after this, and I think it's pretty clear, our Studio Cloud is wonderful. we have this free resource that we can use. It's not a robust solution for doing like real work in R. It's great for small demos, but doing real work in R, it's not a robust solution for that. So probably your next step, if you're new, is go and install R on your computer, install R Studio, and you can go from there. So let's go ahead and retry to make that national map. We should have plenty of memory to do that now. And as you can see, the map is pretty bad. And why is that? Well, part of the United States crosses the international date line. It crosses basically, not the international date line per se, but it crosses the 180-degree line of longitude. And so what that does is by default, it wraps our map. So Alaska's way up here, Puerto Rico's down here, Hawaii's way out here, Alaska's all elongated. We have the Aleutian Islands crossing over onto the right-hand side of the plot. This is not a plot that you really want to show to anyone. And so we need to figure out a better way to do this. And I have a function in the tigris package that is designed specifically for this use case. It's called shift geometry. And so what shift geometry does, as we kind of go through here and take another look at the map, shift geometry, you'll need to reload the tigris package to use it. But what shift geometry does is it shifts and optionally rescales Alaska, Hawaii, and Puerto Rico to alternative positions. It actually moves the data so that you can make national maps more seamlessly. And by default, it ends up, what shift geometry does is it shrinks Alaska, it expands Hawaii and Puerto Rico, moves them all below the continental US, allowing for a much nicer looking interactive map. So let's go ahead and run this through and see what our rescaled map looks like. Mine is stretching out a little bit in my viewport here. There we go. That looks much better. So now I have a much nicer looking map. Now, granted, be aware of this caveat. We have actually moved Alaska, Hawaii, and Puerto Rico to the wrong place. Hawaii is right smack dab in the middle of Mexico now. So do not do spatial analysis after shifting geometry. It is only for cartography, because if you were to then try to calculate what is the distance from Maui to, honestly, I would much prefer this. I could get to Maui I could visit Maui in probably a couple hours instead of a much longer flight. This would be much nicer, but this isn't reality. And we're actually modifying the underlying geometry to do this. So don't do any spatial analysis with this. It's just for cartography, but it makes for a much nicer representation. Now, I've seen some arguments of kind of data visualization practitioners who have said they don't like this representation because it makes the locations no longer true to area. Hawaii is not this big, Puerto Rico is not this big, and Alaska is certainly not this small. Alaska is enormous. And so their argument has been you need to preserve the area of Alaska. I am ambiguous about that. Basically, I have an option in shift geometry where you can actually shift the polygons, but preserve the area. And so what that does then, and if you set preserve area equals true, and there are two different positions you can use for shift geometry, position equals below and position equals outside. If I do position equals outside, it'll put Alaska, Hawaii, and Puerto Rico in their relative locations. So Puerto Rico will be sort of southeast of Florida, Hawaii will be southwest of California, and Alaska will be northwest of Washington, but they've just been moved closer so you can still see them. And so if I run this next bit of code, which I'm gonna go ahead and do, you'll notice that I still have shifted geometry, but Alaska is now actually true to size. So you don't realize how big Alaska actually is, especially because of so much distortion in maps. But now all of these areas are true to size. So you can make proportional comparisons. The limitation is, of course, you're now having to accommodate the size of Alaska with all of the other polygons. So it can be perhaps somewhat difficult to perceive variations in the continental US, but you have both options available to you if you want them. So feel free to experiment with this and try it out. And one great thing about shift geometry too, and a major reason that I wrote it, it actually works for non-tigris objects. So if you actually have data sets, let's say from another source, it should work for that too. It doesn't have to just be used for shapes you've gotten from tigris or tidycensus. And I've tested it out on multiple data sets from other sources, and it works great. Like, let's say you have another data set you want to overlay over counties, you can use shift geometry on that, and it'll put those locations in the right spot. The next piece, so we talked about the problem with national maps. Now we're talking about the problem with water areas. If you live in New York City or Seattle, are there many other examples around the country, the Bay Area, you are surrounded by water. There's water all over the place. And cartographic boundary shapefiles fortunately take care of the official water area for your polygons, but they're not perfect. And they operate mostly on the exterior of states and counties and less so on the interior. And so if you're trying to make a map by default of New York City or of Seattle, Lake Washington is going to be filled in and look like land area. The Hudson River and the East River are going to be filled in and look like land area. And that can be kind of frustrating because it makes your shapes look weird. And frankly, you know, New York City is going to be one of the most mapped locations of any location in these data sets. And so I had a feature suggestion a few weeks ago from a user who said, is there any way to automate this process? And I haven't even updated my book for this. So this is a very new feature in the Tigris package that allows you for a location to, based on a given threshold, remove water areas from your polygons, vastly improving in many cases your maps. So I want to show you a brief example of really what this problem is for a water-rich area like Seattle, so King County, Washington. So let's say we're mapping out the proportion or percent Asian population from the 2020 census for King County. I'm going to run this code through. I'm not going to talk through all of what this code is doing right now. That's right, I need to reload map view. Because we killed our environment before. So let's pull this up. And you see here what it doesn't look bad at this level. But let's zoom into Seattle. Do you see what's going on underneath the map here? This is an island called Mercer Island, which sits inside of Lake Washington. You can't see the island by default. The files do a good job out here in Puget Sound, so it does okay. But on the interior of Seattle, if you look at Lake Washington, you have functionally census tracts in Seattle that are bordering census tracts in Bellevue, when in reality, they're way on the other side of the lake. And so for cartographers working in Seattle, this gets kind of frustrating because this is not representing the location in a way that's really intuitive to people who might be actually looking at the data. And so what the erase water function does is it auto detects a location. It uses the area water function in Tigris, and it auto detects for that function the location for which data needs to be acquired on water area. It then subsets that water area based on a given area threshold. So if you set area threshold equals 0.9, it says only the water areas with a size of the 90th percentile and up. So basically the 10% largest water areas will be retained. And those areas will then be removed, basically like used as an eraser to remove area from your census polygons. So take a look at the difference. Here is Seattle, Mercer Island, Bellevue by default. Now, let's run this through. It can be a little slow if you're erasing a lot of water, if you have a very small area threshold. So just be mindful of that. But now look how much better this is. And this automates this process. I didn't need to find water data. I didn't need to go in and configure it and process it. Now I have data for Seattle that has removed all of this Lake Washington area. And it actually shows Mercer Island as an island. And it actually shows these locations in Bellevue as they are in terms of land area without stretching out into the lake. And so I'm pretty excited about this feature. Just a heads up, it can be really slow. So if you're working on it for a really water rich area, if I had specified a low area threshold, the default value is 0.75. So we keep the top 25%. King County has a ton of water, like a lot. And so if you specify a low water area threshold, you kind of have to wait around for it. Also, the ST transform function transforms the underlying coordinate reference system of your data to a projected coordinate reference system as specified. This is a little more advanced. If you're using erase water, you really need to specify a projected coordinate reference system. Otherwise, it can be really, really slow. So use ST transform to get a projected coordinate reference system. Use an appropriate area threshold for your data. And as you can see, it only took us a few seconds. And now we have a much nicer looking representation of Seattle that much more accurately represents, how people live in this region. So this is a brand new feature, just came out in the last month, and I'm pretty excited about it. The last piece, and frankly, I don't think I have the computing power to actually run this on our Studio Cloud, but you're welcome to try it out, is erase water is built into the new as.density function for what we call dasymetric density mapping. So a common criticism of density mapping is it scatters points randomly within a census tract. But we know within census tracts, there are locations where people don't live. And those locations could be, many industrial areas, airports, parks, unpopulated areas. Those are not always, that's not always information you have immediate access to. You'd have to go and find that information. But we do have the erase water function. We know people don't live in water areas, and that is the biggest offender. So if I were making a density map of Seattle, for example, using this data, I'm putting a lot of dots in Lake Washington. And maybe if I'm zoomed out, that's okay, but it's still probably not. Because if I'm showing this to someone in Seattle, they'll immediately look at it and say, why are there so many people in Lake Washington? And they might say, well, the dot density algorithm randomizes points within polygons. They're tuning me out because I'm getting way too technical. They just want to see dots in locations where they know dots actually are. So you might want to get rid of that water area. So erase water is baked in with the argument erase water equals true. It defaults to false in as.density. But if you specify erase water equals true, you'll build what's called a dasymetric density map. Or you'll perform, I should say, dasymetric placement, which means that dots will avoid being placed in water areas based on the area threshold that you've specified. And so in Minneapolis, if you've ever been there, there are a ton of lakes, just lakes everywhere. And so if you build out a density map like we did before, we were definitely putting dots in lakes. It wasn't a huge deal in terms of showing the overall representation, but if we were to put a base map under it, which we'll commonly do, we'll have dots in lakes, and people are going to look at it and say, yeah, I don't know if this map is accurate. You just put a bunch of dots inside of Lake Minnetonka. So the erase water equals true argument, and I'll be honest, it's a little computationally intensive, and because there's so many lakes in Hennepin County, this code will take a little time to run, so I'm not going to run it right now. But what it'll do, and I'll show you the result of it, it will first remove the water area from the polygons and then randomly place the dots within the polygons. And what's great about that is look at all of the lakes here. This is Lake Minnetonka to the west of Minneapolis. There are all these little suburban towns in all these inlets around the lake. You'll notice all the dots are only on the land areas and they're not in the water areas. And in the city of Minneapolis, you have some large lakes here in Southwest Minneapolis. You note that we didn't put any dots in the lakes. We only put them around the lakes where people actually live. So I'm pretty excited about this feature. If you want fast dot density maps and you're not worried about putting dots in water, just use the defaults. It'll be really, really quick. If you have a little time to spare, and usually it's only 30 seconds to a minute, it's not terrible, depending on how water rich the area is. Use erase water equals true, and that's going to get you dasymetric dot placement that you can go in and use for your dot density maps and offer a more realistic representation of where the dots are located. So this is all brand new stuff. It's not even in the officially published version. I haven't written about it anywhere. I need to go and update my book now. So you are really the first to even see this or hear about it. And Chris mentions parks and cemeteries. Great point. I don't have that data in Tigris, and so that's why I don't include it. So there are other methodologies where you would need to do pre-processing, and maybe in the future, I'll allow for an option that basically says, here's a layer, and you can supply an arbitrary kind of secondary layer. Like if you had a data set of parks, you could go in and you could supply it. I just haven't implemented that. Maybe that's a future improvement. Part of the fun thing about open source software is this stuff is always evolving and it's always changing. And even with this workshop, I was thinking about it. I thought, oh, I want to show dot maps to everybody, but it's really slow. And then I discovered this other new functionality for generating dots. I thought, well, let's just put this into tidycensus. I think people will use it. And then I thought, well, it's still placing the dots that, I was testing on Manhattan. It's placing dots in the Hudson River. I really need to put water erasing into this. And, now it's creating something that honestly, I'm going to use this all the time. I'm really excited about it. And so, and I've been very happy to show it all to you. So that concludes our material. We have a few moments left for questions if you have them. A couple exercises that you can go through. First is take a static map you created in part 2 of the workshop and do tmap mode view to make it into an interactive map. And then also try experimenting with shift geometry. So using the example that I showed you. So there are other combinations you can try, different combinations of preserve area and position arguments, a couple of which I didn't show you. Try out those different combinations and just kind of think about which layout you prefer and why you prefer that layout, because you do have different arrangements that you can specify. So yeah, that concludes our information for today. Really appreciate it. So if you enjoyed this workshop, come back next Friday. It's going to be first look at the 2016 to 2020 American Community Survey data. They were released yesterday. If you're an experienced tidycensus user and you know about the get ACS function, just put in year equals 2020 and it's going to be working already. I don't have it documented anywhere. I need to do that, but that's all coming next week. It would be great to have you back, and happy to entertain a few moments of questions. So I've got the chat up here and looking at some questions. And JP, if you have anything you want to jump in on as well, just let me know.
Yeah, so I see one question that that just came in about when the video will be posted. So we faced a couple delays getting the one up from last week, but we will send out something hopefully within the next couple days, maybe even by tomorrow, with the video from today's session, and if you have not already received an email, the video from last week's session as well.
All right, let me just grab a couple of these questions here, and then if you see any other good ones, JP, feel free. Ralph had a question about ZICTAs, so zip code tabulation areas for 2020 census data. As of right now, you cannot. It's frustrating, I think, for a number of people that I've seen posts about online. Just about all the other geographies are available for 2020, but the ZICTAs have not yet been incorporated into the 2020 census data. I imagine they will be at some point, because we can get 2020 ZICTA shapes, because I know it took a little while for those to be defined on the tigris side, on the tiger line shape files. And those were just released. So it may be that census is currently doing the tabulations for ZICTAs. But no, I double checked that, and it's not yet available. A couple questions about the dot density function and how it works. Again, this is brand new, so I totally get it. It's not documented anywhere. What you'll need to do first, if you need to have the GitHub version of tidycensus installed. And so if I put in package version tidycensus, it should be 1.1.2.9,000. That means you have the GitHub version installed. The way that you install that is using the install GitHub function in the remotes package. And so I can do library remotes, install _ GitHub, and then in quotes, Walker KE/tidycensus. That may take some time to install depending on your operating system. And so allow that to install. And then once you have that installed, look up using the question mark sign as.density. I've tried to be fairly comprehensive in the help documentation for this because I haven't written about it anywhere else. And it will tell you how it works. So you can read through, it'll explain to you kind of the underlying process, how you deal with groups, how erase water works, how to improve performance. There are a couple of things about it that are important for you to know. I see Rick's question about what as.density does with respect to randomized display. It randomizes 2 times. The first time that it randomizes is within a given group, it places the dots randomly within a tract. So if, let's say, for example, you have census tracts and you're mapping random population, what it'll first do is it'll take the population and then it'll basically do integer division and divide by the values per dot value. So if I have 1,000 people and I want, say, and my values per dot is 10, then I'm going to draw 100 dots. I take those 100 dots and I scatter them randomly within a census tract relative to a random number seed, which you could set beforehand if you want to consistently place dots. Then what it'll do is it steps through each group. So basically, if you specify a group, as we did, it'll take the group. So it'll take Hispanics, randomly place the dots for Hispanics. Then it'll take the white population, randomly place dots for the white population, and so on and so forth, and then combine the result. One issue that can come up, however, with combined dot density maps, and in ArcGIS, this is a big problem with their implementation, unless they've since fixed it, and I haven't seen that, is they stack the dots by group. And so you'll have the group on top occluding the dots in the bottom group. What my implementation does is it randomizes the order of all the dots before giving you the dots back. So the dots are not only randomly placed within the polygon, but also randomly stacked on top of each other. And so this improves display significantly. The last caveat about as.density. So as.density has a soft dependency of the Terra R package. What that means is that when you install tidycensus, Terra does not install by default. And the reason why that is because Terra is sometimes slow to install, and it's a very big package, and I only use one function from it. So you'll get an error message if you don't have Terra installed that the function uses Terra to generate the dots. You need to then go install it separately. Once you do that, the function will work. I see another question about erase water. Erase water is in the tigris package, not the tidycensus package. So you'll want to install tigris with install.packages tigris, and then you'll get access to erase water. And so, yeah, I think, JP, if there's anything else you wanted to follow up with.